All right, so welcome back. Today we're going to continue on functions and methods in Java. We left it off last time with a demonstration of how to do this in C. Remember that over in C, what we did was we separated things out into prototypes and definitions. Remember that we are on online, so if you're on Piazza or the YouTube channel, go ahead and post questions there. Otherwise, what we did is, and I did a little bit more after we left, we created this round to sense function, right? And we also created, what I did offline is I created this get monthly payment. Because remember that was like, it's not a super complicated formula, but it might be something that we might want to use and reuse. Even though in this particular program we're only using it once, there might be other programs in which we want to compute a monthly payment, a mortgage application, whatever, a loan, auto loan application, etc. These would all basically use the same formula. So I put that into another function down here. We had the prototypes up top because in C, you need to declare a function before you can use it. And we also tied all of the documentation to all those prototypes. Then down below, what we did is we put these into, made the actual function definitions at the end, all right? Let's see, let's make sure that this actually compiles. What is it, loan, and then -lm, right? And it actually runs. I won't actually run it too often here because it's the exact same thing that we did before. The $10,000 at 5% interest over 5 years, etc. Right? So again, functions in C. What do each one of the things that we went over, right? In general, every function should have documentation, doc style documentation, all right? And this is in C here, which is associated with the prototype, all right? Don't stick documentation with both the prototype and the definition, right? The DRY principle. Do we remember what that stands for? Don't repeat yourself. All right? I just repeated myself by telling you what the DRY principle is, though, right? All right. So, what are some other observations that we've had so far? The prototype has no function body, right? It ends with a semicolon, right? Remember that over here in C, right? It ends with a semicolon. What else did we might observe from it? How did I name my functions, by the way? What casing convention did I use here? Lower camel casing, right? So, convention, I'm going to be using the lower camel casing convention. That is definitely standard in Java. Some variations, there are some variations in C. One thing that you want to stay away from, though, is upper camel casing. That screams out to me that it's C#. That's a standard in C#. Not many other programming languages do that. And again, these are not rules. These are just guidelines. Okay. In general, functions should have be verbs. Oh, I already wrote that, I guess. Right. In general, they should be verbs. Why? They do things, right? And what is a verb? It's an action word, right? Other variables that you create are nouns, right? Person, place, or thing. Monthly interest. Well, how do you compute the monthly interest or get monthly interest? Remember, there are only two difficult things in computer science: cache invalidation and naming things. So if you're having trouble thinking about a name for, well, compute the monthly interest, the usual thing to do is to slap a get in front of it. Get the monthly interest, right? You can put compute in front of it if you want to, but you're already on a computer. You don't need to repeat that you're computing stuff, right? So it should be a verb, right? Later on in your program, you provide the function definition. You repeat the prototype without the semicolon, and then provide the function body. All right? The code in the function body is what is executed when you call or invoke. Both of those are terms that we use when we're talking about functions. The function, right? Function. Right? Control flow is handed over to the function, and it computes until it gets to a return statement, right? At which point, at which point control is given back to the calling function, all right? And this is how it works, right? These are called, sometimes these are called subroutines because you've got the main routine here, and then you, I want to call this function. You hand control over to that function, a subroutine, so it executes over here. Well, you need to get back, right, and continue your routine. And so that we call that the calling function, and the subroutine or the function calls or invokes that subroutine. Okay. Let's see. Another observation. Any variables declared inside a function are local to that function. Right? Looks like we're doing all right. And they have local scope to that function. Right? And what do I mean by this? Now, we never declared any variables in here, but I could have. For example, I could have said, say, double. Is this large enough for everybody in the back? Or, okay. Double result, right? And I could have stored that rounding value into a variable called result, and then I could have returned that result, right? Result here is a local variable. It exists inside this function, and it only exists inside this function. Let's go ahead and look down here to this function. Do you see, in the context of this function, in the scope of this function, do you see any variable named result here? Nope. Do you see any variable named result up here in the main? Nope. If I tried to printf %f result, right? If I tried to refer to that variable that exists in that other function, it's not going to compile, right? Because it has no idea what you're talking about. Main has its own variables. Round descents has its own variables. Get monthly payment has its own variables. We've sequestered all of the variables in a function off to itself, right? So that they're not stepping on each other's toes. Result does not exist after control flow is given back to this function up here, if you're calling round descents or something, okay? By the way, I did it right the first time. Is there a need to create a local variable here? Nope. Just have it do what we did before. Just return that expression. Okay. Now, if there is a more complex function where you've got, say, 20, 30 lines of code, and you have need of local variables, whatever, then it's perfectly fine to create variables. You don't have to minimize the number of variables just because you can. Okay. Readable code and understandable code is far better than one fewer variable code. Okay? All right. What about Java? We'll come back to this here. Right? Functions in Java. Technically, functions are called methods in Java. Don't worry about the distinction. You'll find me calling them functions all the time. The only difference is that functions can exist out in the global scope. In the math library, there's this function called sqrt. Over here, we've got this function called round descents that exists. Right? It just exists as a function by itself. In Java, however, everything is a class or belongs to a class. The square root function, where does that exist? In the math library. That's why you have to go math.sqrt. It has to belong inside of a class because it's object-oriented programming. When a function exists inside of a class, that's when we use a different term and call it methods. It's a method that you can call, okay? So don't worry about that distinction. Again, it's an object-oriented programming thing that we'll get to eventually, right? For now, we'll restrict our attention to static methods, right? Methods, all right? Methods that belong to the class, right? You don't have to worry about what that means. Just worry that to invoke a function or method, excuse me, you need the class name plus the dot plus the name of the function, right? And let me go ahead and indent this. Example, the classic example here is math.sqrt. What about our example here? Technically, if I've got a round descents and a get monthly payment, and now I'm in Java here, right? How do I invoke those things? Let's go ahead and get rid of this right here, this long formula, and let's go ahead and call that function up there. Now, technically, I could get away with just get monthly payment here because I'm already in the class. Get monthly payment, I'll pass in the annual rate, the principal, and the number of years, and then get rid of everything else. Right? So much cleaner when you hand that complex formula off to another function, right? So I could technically do this and get away with it, but that's because I'm already in the loan class, right? What if this function or what if this method were in a different class? Or better yet, how should I do this? Like I did with the round descents last time. Loan dot, the class name dot, and then the function name, right? And as we saw last time, if I don't make it static, that means that it doesn't belong to the class. It belongs to instances of the class, and I would have to create a loan class just so that I could call this get monthly payment. You see down here that it's not going to compile anymore, right? So for now, we are going to only stick with static methods, right? Public, static, whatever, right? And by the way, what does public mean? Static means that it belongs to the class, but public means that anybody can use it, right? So public methods can be seen and used by any code in your project. All right? So, yeah.
Global somewhere? Is that in JavaScript or?
Global?
Yeah.
There's no keyword global in either language, I believe. But you can have global, yeah, I mean, there are globally scoped variables in both languages in some sense. With C, a global variable would be, over here in C, a global variable would be a variable that you just create globally. Int foo. Now everybody can see foo, everybody can change foo. That's not what you want, right? You want to limit the scope of your variables as much as possible. So globals are evil, right? Now, how do you do a global in Java? You can't really. You can create a static, say a public static int foo, right? Now, everybody can see that variable, but it still belongs to the loan class. It's not outside the loan class. You cannot create a variable like that at all, right? You can't compile that, right? Globals are evil in both languages. Now, there are some languages where, by default, if you just create a variable, for example, JavaScript. If you create a variable, it's now a global variable, right? Right? Yeah. You have to put var in front of it in order to make it a local variable. Var is short for variable. and that locally scopes it to that function only. Programming language like, say, PHP is just the opposite. You can create global variables, but if you want to refer to them, you have to use this keyword global in front of it. Python is the same too. You can create global variables. It's not a very good idea, though. Right? In any language, it is not a very good idea. The reason being is it is far less predictable code. If you create a global variable that every piece of code can see, that means that every piece of code can change it. And if every piece of code can change it, there's no protection for that variable, right? There is no predictability, right? Now, globals are okay if they are constants, right? Math.pi, right? Nobody can change that. If I tried to change that, let me try to change it. Math.pi is equal to 4 now, mysteriously, right? That ain't happening, right? Because it is a final variable in Java. Likewise, over here in C, there are global variables, for example, m_pi. It's technically not a variable, though. It's actually a preprocessor directive, a macro, where the preprocessor goes through and cuts and pastes. Remember, we looked at this very briefly with define, right? Define ems of pi to be 4, right? And that definition now conflicts with the math library. I wonder if they'll still even compile now, right? Okay, well, I need to get rid of this thing that I did down here. Let's find out. Yep, this is the location of the previous declaration. So over there in the math library, they defined it out to this much. And of course, they've got a nice little comment here telling us, that's pi, by the way. Oh, gee, I wouldn't have known that with a name like m_pi, right? But yeah, I've redefined it here, and that's why it's giving me a warning or a note, just a note, and just a warning. Right? All right, you can go ahead and redefine pi if you really want to. Right? Don't do that. Okay. All right. So for both languages, I guess elsewhere in the, let's see. Some alternatives here. I'll just go ahead and make sure that you've got these. Some alternatives would be private and protected. If it's private, only the class can see it. In other words, the lone class in this case. If it's protected, only the class and subclasses can see it. But again, we're not going to get into object-oriented programming until later, so don't worry about it. There is an absence of a keyword. If I didn't have a keyword here at all, if I just left it like that, that's called package protected. Any other class in the package can now see it, right? So it's a hierarchy of visibility for these things. In general, though, I mean, there's no problem with making methods, static methods especially, public, right? If you want other pieces of code to have access to your functions or to your methods, right? Okay. So some other issues before we get into modularity, right? Other issues slash items, right? A method or function that doesn't return anything is a void function or method, right? You can make the return type void, right? And what is void in plain old English? Nothing. It returns nothing, right? You can make the return type void to indicate that it returns nothing, right? Best practice, you should still have a return statement. Even if you're not going to return anything, what you do is you say return, and then you put a semicolon there. So what am I returning? Nothing, exactly, right? Both languages allow you to do this, right? You can also have a function with no input. You can create functions with no input, right? You just don't use the void keyword, right? You use blank or empty parentheses, right? So for example, say You could use the void function if you void keyword if you really wanted to, right? I believe both languages will support this. We can try it. Let's go ahead and try it. Over here in Java, I will make a public static int foo void and return 10, right? So Java won't even let you do this. The preferred way anyway is to just leave it blank, right? That's even more of a void than using void, right? Now over in here in C, you can, right? You can, this will, well, not with static, not with public, but this will work perfectly fine, and this is almost nearly equivalent. There is a small little difference that we won't get into. It's whether or not the compiler can figure out what you're talking about. But this is the preferred way of doing it, just leaving it blank parentheses there. I don't take any inputs. I simply return 10. And if you think about this as a math function, what does it look like? Just a horizontal line. Right? It doesn't depend on the input. It doesn't depend on x. Okay? But you can have void functions. You can have functions that don't take anything. Right? Another issue is what's called function overloading. Right? And this is super important as one of the major distinctions between C and Java. In C, how do you compute the absolute value function? Abs, is that the only one? There's also fabs, labs, lullabs, and maybe a half a dozen other ones that are there, right? What is the difference between abs and fabs? Yep, fabs, f being the floating point number. So it takes a double and it returns a double. Abs is going to be for integers. It takes an integer and returns an integer. So if you want to take the absolute value of negative 10.5 and you use abs, what is it going to give you? 10 because of integer truncation. You have to be careful. If you use a long, you have to use labs. That's what the L stands for. If you use a long, which is usually a 128-bit number, right? Then you use lullabs or LL labs, right? Long, right? Why in C do we have to have different names for functions that essentially do the same thing? They all take a different type and they return a different type, right? In C, you can only have one function with one particular name, right? In some languages, say Java, you can have multiple functions, methods, with the same name, but with different return types, or with different parameter types, I should say. So, for example, in Java, the math library contains 4 different abs methods, all with the same name. Now to prove it, let's go ahead and try, I'm going to go ahead and take you there. Let's see. Let's go with math.pow. Right? So here's the actual code in the math library in Java. Let's go ahead and search for all of the abs methods. Right? There we go. Nope, so public static final. I don't know if it's going to be final, so public static. No, I want abs. There we go. Where are you? Come on. All right, take me there. There we go. There's the long one. I'm sure right below abs exact. Abs exact. There's the other one for integers. Right? Takes an integer, returns an integer. But the name is exactly the same. ABS. Floor mod. That's not what I want. What else? Abs exact. Abs that takes a float and returns a float. Abs that takes a double and returns a double. Right? And I think that's all of them, right? That's 4 of them. One for doubles, one for floats, one for integers, one for longs, right? The 4 different built-in numerical types in Java. So why does Java allow this and C doesn't, right? Java allows and supports method or function overloading, right? The ability to have multiple functions with the same name, right? C does not. At compile time, the Java compiler is able to deduce which function you intended to call based on what you pass it. Right? And what I mean by that is if you call math.abs and give it an integer, oh, you probably meant to call the one that takes an integer, right? Pretty straightforward. You call math.abs on a float, oh, you probably meant to call that other one that takes a float, right? The compiler, the Java compiler, is smart enough to do that for you. For historic reasons, the C compiler is not smart enough to do that. In C, in fact, a dirty secret that I'll tell you about C is that you don't actually need prototypes. Bad things happen if you don't have prototypes, though, because then it starts guessing. Without a prototype, oh, you called this function over here called square root or round descents. I'm gonna guess that it's that one over there, right? And oh, well, it takes an integer, but you passed it a double. Okay, some rules now apply that you don't know anything about that's happening under the hood. I'm going to make assumptions about the return types, and the assumption is that by default they're all going to be integers. Right? Bad things happen, weird things happen. You'd have to read the actual spec in C to understand what's going on, because there are a bunch of rules that happen when you don't have prototypes. I don't want to live in that world. Use prototypes. But as a side effect of that, we don't have function overloading in C. Right? In C, you only have one function with that particular name. Right? This mechanism is called static dispatch. Now, it has nothing to do with the keyword static that we've been using in Java. Static simply means, in this context, static means at compile time. And dispatch means, okay, which function did you mean to call? All right, you passed in a double. All right, I'm going to dispatch it to that function over there that takes a double. Right? And that's what that's the idea there. And again, C does not support function overloading. Once you've created a function with a particular name, that's it. That's the function. You cannot create another function called sqrt because the math library already does. Right? You have to be careful though. All right? Suppose that I use, in C now, because of this limitation, what if I pull in a library with a function called create widget? Right? And then I pull in another library, or create list, say, because a list is more common. Create list. Library A has a function called create list. I pull in another library that I really want to use, but it just happens to have another function with exactly the same name. Can I bring both of these libraries in and use it at the same time? Nope. And it's even worse if I create my own function called create list. Right? Now I've got two libraries that have the same function name, and I want to use that function name too. Right? What's happened is that the namespace has been polluted. Right? And you have to be careful about that. In C, you end up polluting the namespace. Once you create a function with a particular name, that's it. You can't use any library that defines a function with that name. You can't use two pieces of code that use that same function name. You've polluted it, right? You've polluted the namespace of functions, the names of functions. And you can't ever reuse that function. So the trick, the workaround that is usually used, is if you're going to write a library, you prepend it with a tag, right? So say I created a library called the Burke library, right? I would put in TBL and then before every single function. TBL underscore create widget. TBL underscore create list, right? And it gets kind of tedious, but that's the basic workaround. Good libraries do that all the time. At the end of the semester, you'll see one called GTK, which stands for the GNU, or the GIMP Toolkit for creating graphical user interfaces. And every single function in that library begins with GTK, GTK, GTK. And it's because it doesn't, they didn't want to conflict with any other libraries. Okay? All right, let's see. Those other issues. All right. Questions so far? Then let's go back to the C example over here. And I've got two functions, right? Now, this isn't that big of a deal. There's only 60 lines of code here. But now think ahead. Suppose that I've got a really complex program with hundreds or thousands of lines of code, dozens or hundreds of different functions. Do you want to be storing everything in one big giant file? Nope. C doesn't do that. What does C do? C takes stuff that is in the standard library and it puts it into a separate area, a separate module containing those functions. It takes functions related to the standard input-output and puts those into a different module, a different header file. This is what the H stands for here. It takes the math functionality and puts it in yet another place. It separates things out and organizes things into modules. And that's what we're going to do now. We're going to start out in C, and then by the end of the day, we'll go over to Java and do the same thing, right? So modularity in C. In C. There we go. In general, similar functions are separated into different modules. Right? And the reason why you want to do this, why? Organization, right? First of all, but also not sequestration, but sequestering things, basically. Keeping things separate is good. You only need to bring in particular libraries when you need them. Right? You could, of course, I'll just import everything, right? You don't want to do that. And by the way, in Java, we haven't seen it yet, but hopefully we never see it. If you want to bring in something, right, you use import. There, I just imported the entire Java code base, or Java dot. I just imported everything. Java.util. I can do that, right? There we go. Now it finally compiles. I'm bringing in absolutely every single utility in the entire language. Is that a good idea? Now, be more intentional, right? You should only bring in that which you need. This is called a wildcard. Bring in everything. Don't do that, right? If you need to bring in a scanner, then bring in a scanner. If you need to bring in a list, then bring in that list. Don't bring in absolutely everything, especially if you're not using it, okay? All right, so organization, and finally code reuse. Why did we make functions to begin with? Why did I make this round to sense function over here? So that I could use it in 1, 2, 3, 4 different places, right? Well, if it's useful to me in multiple places, maybe it's useful to other people in other places, right? For example, the math library, right? They probably thought, well, sine, cosine, square root, those are things that are probably going to be useful to many, many different people. What we'll do is we'll take those and put them into a library and then publish that library so that everybody can use that library. We're going to do the same thing, right? Code reuse. You can then publish your code as a library so that other people or other programs can use them. Right? This has to do with a loan amortization table, right? What if you had a mortgage application, or what if you had a student loan application or something like that? These probably seem like utility functions that seem to have use beyond just this loan amortization table problem that I just solved, right? Okay, so I'm going to go ahead and demonstrate how to do this in C. Demonstration. Right. we're gonna create our own financial utilities library. Okay. I'm going to demonstrate it and walk you through the process, and then what we'll do is we'll come back and note how the step-by-step process for doing that. Okay. So first of all, the first thing I'm going to do is I'm going to create my own header, what's called a header file. I'll just call it utils.h. If you want to, you can call it financial utils.h. Utils.h. What is utils short for? What do you think? Utilities, right? And I'm also, so this is .h is a header file. You've seen this already. Math.h, stdio.h. There are header files throughout the system, right? Let me go ahead and open this up. What am I going to put into this header file? I'm going to take all my documentation, which is associated with all my prototypes, and I'm going to move it over here. There. Now my main code is far less cluttered. Up here, we brought in those header files by using the include statement. Now, because I no longer have those prototypes here, I need to do the same thing. I will include utils.h. Oh, wait a second, that's different. I'm using double quotes here, right? Why? The Langle-Wrangle, we call that Langle-Wrangle, not less than and greater than, right? Why would we call it Langle-Wrangle? Left angle bracket and right angle bracket, exactly. It comes from LaTeX, a typesetting system. Anyway, those denote that, hey, this is a standard library. Standard library, standard input-output library, standard math library. Go and look on the system in the area that corresponds to all the standard libraries. And the compiler says, great, I'll go ahead and look there. If it doesn't find it there, then it will look in the current working directory. Right? By using these two, the double quotes here, what I'm saying is this is not a standard library. This is a user-defined library. Don't bother going to look in the standard library location. Look immediately here. Right? And that's the only difference. It saves the compiler some extra work. Yeah?
So why isn't math called like STD math?
That's a good question because I think it's historic reasons. The same reason that we sometimes have to use the -lm flag is because they didn't want to make it standard. They thought, oh, everybody's going to want to write their own square root function, right? So we shouldn't have a standard one. We should allow people to, make their own math libraries. That was their thinking at the time. Don't quote me on that. I think that might even be apocryphal. I don't know. But good question. There are plenty of other libraries that don't have STD in front of them. Include the string library, for example, right? It's not STD string, it's this string library. Right? Another question? No? Okay. All right. And you can see here that this will actually compile just fine here. Oops. Where am I? I'm not in honors anymore for some, but there we go. All right. It'll compile just fine because the way that header files work is this hash right here, remember, is a preprocessor directive. The preprocessor goes, just like define pi to be 4, it goes throughout your program and finds all instances of pi and cuts and replaces that with 4. Right? It's doing the same thing here. The preprocessor, what it does is says, oh, okay, you want to include this library? It goes out to that library, cuts and pastes and replaces that statement before it compiles. Right? We don't have to worry about that because it's much cleaner to do it this way. The preprocessor takes care of that for us. Okay. Now what I'm going to do is I'm going to create a source file, new, with the same name, utils.c, because utils.h, utils.c, same name, means that there's a connection to it. If I called it utils.h and then random other file.c, right, is there an implicit connection between those two? No. So I'm going to use the same base name, but .c. And we've seen .c already, right? Lone.c. It is a source file. And what I'm going to do with this is I'm going to take all of those definitions and move them over to that source file. Right? Now, before we go any further, do you see any prototypes in this file right here? Nope. We want to live in a world where there are always prototypes, remember, right? We don't want to live in the well, I guess what would it be, 1980? Yeah, late 70s, when prototypes were optional, right? We want to live in the modern world here. So what I'm going to do is I'm going to bring in those prototypes. How? How do we do it over here? We included the header file. Now, in this file, do you see anything else we need to include? We use a function called round. We use a function called pow. Do you see those prototypes anywhere here? Nope. I need to bring those in, and which is what we've been doing this entire time, by including standard libraries like math.h. Yeah? You could. There are libraries that do that. They're header-only libraries. In fact, they try to bend over backwards to do everything with the preprocessor so that they have almost zero code to be at all. Some people like that because it means all you have to do is download one big giant file, and you don't have to install, say, if it's separated out into 50 different source files, you don't have to install an entire thing. Usually, I mean, there are arguments for and arguments against something like that. There are also projects that will build a header-only library. So they'll follow the best practices and separate everything out into header files and source files, but then they'll also write a script that goes out and changes everything so that it's just one big giant header file. Nobody's ever intending to maintain or read that or do anything with that other than just use it in their compilation process. This code over here, that's what you read and maintain and all that stuff. And the script just produces a more easily downloadable file for it. So yes, you could do that. It's not, I mean, doing that directly is not necessarily a good thing because now it's kind of like what's called a God anti-pattern. So if you've got one file with all of your functions, right? Now it does everything, it knows everything, it sees everything. That's the God file, right? It's not as maintainable as if you separate things out into different modules, right? It's not as organized either, right? You've got one big giant million lines of code file. Gross, right? Okay. There is my library, right? Now, let me try to compile this loan again. Uh-oh. It doesn't work anymore, right? It says, I don't know anything about round descents. I do know something about it because I know it exists, but I couldn't find it, right? This is exactly the same error message that you would get if you left off the -lm flag, right? You would just get it about, and I'm not using any math anymore in this file, but these are the same exact undefined references errors that we got when we don't include the math library properly, right? Why? Because we've moved them into an external library. So what I need to do is I need to make sure that I compile that library. Does anybody remember that flag from the first week? -C. What do you think it stands for? Compile, right? Compile the utils.c file. Okay, I did. What did it produce? A .o file. Do you remember what that stands for? Oh, an object file? It's not a text file, right? In fact, we can look at it using this other utility called less. Yes, I'm sure. I want to look at the inside of that file. Is that anything that makes sense to you? Nope. It's just a bunch of machine code. Right? It won't even let me open it, by the way. Right? No, you can't open that. Right? I can ask what type of file it is, though. Is an ELF 64-bit LSB relocated, blah, 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 blah. It's just an object file. It's just a bunch of machine code. Right? Somewhere on the system, there's a similar math.o file. Somewhere on the system, there's also a similar stdio.o file, object files. Right? And that's how these things are actually stored and maintained. Right? Now, to bring it all together, I need to compile yet again. I compiled that utils file that produced an object file. Now, normally, what you're used to at least is using this -lm flag, right? I'm not going to use the hyphen library include the utils, right? It doesn't know anything about that. That's for standard libraries, or installed libraries, I should say. Instead, I'm just going to say, use that utils.o file that I just compiled. Right? And now it produces that a.out file that requires input. Right? Question?
Yeah, so when we're including a header, whatever we actually include.
You are telling the preprocessor to go out, grab that file, cut, and paste it right here.
Okay. So
And-
we have the thing you put before.
The preprocessor is automatic. I mean, there might be a flag that says only run the preprocessor,
Okay.
but that's kind of weird. Yeah, I don't even know. There might be a flag for that, but
The actual function is not in the header.
correct. The actual function is over here in the .c file.
Okay.
Now, I hesitate to show this to you because do not do this. But you can, I mean, it's an arbitrary thing. You can include whatever file you want. When I do this, I can go ahead and just compile everything like I did before. Lone here. Of course, with the -lm flag for the math library. Why does that work? Because the preprocessor says, okay, I'm going to go ahead and cut and paste everything in here into that file over there. And suddenly now it has those definitions. Right? Don't do that. You do not generally include source files because you could do something like this. I'm in the lone.c file. If I include the lone.c file, what's going to happen? It's going to go out and cut and paste this entire copy, paste, and guess what? Copy, paste, guess what? Oops. Copy, paste. No, I don't want to do any of this. So I'm going to go ahead and go undo all of that stuff. Right? Utils. But let me show you what happens when you do something like this. Oops. Oh, come on, really? Save it. All right, you're smart. Whoa, you are smart. All right, it's no, utils.c, lone.c, lone.c. There we go. Now let's find out what happens. Did you see that? It's still going. It's an infinite kind of thing here, right? So, all right, let's stop that and let's go back to what you should be doing, only the utils.header file, right? You can do something like that, but you should not, right? You don't generally include source files, all right? Yeah?
So when you compiled the util.c, why does it give you .o?
Because it's compiling, do you see a main over here? Nope, so it can't create an executable a.out file, right? It's just a bunch of functionality that exists that you can link into your executable file. Just like math.o, or math.h, math.c, math.o, there's no main there at all. Because if it had a main, then it pollutes your namespace. There can only be one function called main. If the math library has a function called main, you can't have a function called main. You can't even compile stuff. Right? You can't compile it into an actual executable. Right? Yeah.
So is the preprocessor copying and pasting that header file into utils.h, and then
Yep.
what with that .c file, when it becomes a .o, does it then copy and paste that into every place that function exists in your?
No. No. It only exists in this file right here, utils.o. Right?
So it's more pushing the inputs and returning.
Think of it as compiled machine code, right? I've got my two functions over here, and I compile them. Here's the machine code for that. I've got my main, and I can compile that. I can, in fact, compile, but not GCC. Compile, but don't create an a.out file of loan.c. Right? And you can see that I've got loan.o now. Oops, come on. There's now a loan.o file. That's just my main that is a bunch of machine code. I still don't have an executable. I have this machine code over here, this machine code over here. I have to link them together in order to create something that can actually run. Right? So the way that you should think about this is just a bunch of machine code that you can use if you want to. Right? Does that answer it? All right.
Yeah.
Okay. All right. Yeah, go ahead.
So the dot H is like the paper, the thing that you write before you write.
It's a header file that always includes the prototypes.
Prototype.
Prototypes, and if you've got other preprocessor stuff like define, exchange rate, right? Like $1.5 to yen or something like that,
So
right?
can you technically don't include a header file, just write the program?
Yeah, that's what we did before. That was what we started out with.
Okay.
But that means that you're not writing modular code. That can't those functions can't be reused by another program, right? It means that you've now gone down the path of the God file, where everything is included in one file and one file only.
Okay, but when you like create a .o file, but you create
Preprocessor directives,
no,
like
the one you just mentioned where you declare the function in the beginning.
yeah, you can do you can do that, yeah.
Okay, and then you link to a .o file.
Yes.
So you don't include .o file.
You could do that. You could do something like this, where we don't include the .h file, but we just have the prototypes directly, not the definitions, and then it follows the same process that we just did.
Okay.
The only difference is that now, we're letting the preprocessor take care of that junk for us, right? Which is much better than having prototype, a million prototypes, put them into different files, include them, and let the preprocessor deal with it.
Okay.
Yeah.
We include the utils.h file. What is running us have access to the utils.c?
It does not. It has no idea what the .c file is. It only because it's the difference between declaring a variable and using a variable. Prototypes are only declaring this function. It's not declaring. It's not telling you what it does because there's no body. So the compiler says, okay, yep, I see. Oh yeah, I know about this get monthly payment. It takes 3 inputs. The first 2 are doubles, and the last one is an integer, and it returns a double. I don't know what it does. I don't know where the code is for it. That's the compiler's problem, right? The compiler cannot find it by itself. That's why you have to use GCC, include this .o file because that's where it is, and compile the loan.c file, and also include the math library because that's where it is. If I didn't have that, then it wouldn't know where is that thing, right? Undefined reference, right? Now, it's automatic in the sense that here's the object file, it's in that. Okay, great. And it goes inside the object file and looks for it, and it finds it eventually, right? And you can kind of see that here. If I go with that less utils again, yes, it is a binary file, but it contains some plain old English. Yes. Do you see round descents right there? Right? The compiler is able to go in and say, scan that input file, that object file. Oh yes, there's the round descents. I found it. Here's the machine code to link in and bring it and include in my compilation process. Likewise, get monthly payment is right there, and round and POW, right? It's got all these references that you can actually read because it's just that's not machine code. Good questions. All right. Any others? No?
Is there a map? Can you just, instead of doing the LM flag, can you just do math.o?
You could, but you wouldn't want to. I have no idea where it even is. Ubuntu find GCC standard library locations. I'm probably technically not even math.o somewhere. Shared libraries, where to look for shared libraries. We can try this. Oops, no, go over here. So maybe in the lib32. Actually, no, it's going to be 64-bit. User local lib, no. Default configuration, so let's look over here. Open, oh, I can. Okay, it might not let me start mucking around with the actual system files here. Lib x86. All right, and is there any math there? Nope, Maria, that's a, is there standard? I don't know. That's a lot of libraries, yeah. These are all external libraries though. What else, where else are they? ls user, no, that's the local. User lib x86. No, I think, well, that might be the same place I just looked. ls lib 32. All right. cd lib 32. Is there any math? Nope. ls lib math. M might be the math library. File lib m.so. SO is shared library. Okay, it's a symbolic link to that one. File lib m 2.30. Okay, we're getting closer now. Let's go ahead and less this. And if you see SQRT somewhere in here, nope, it's not in there. But if it were, yeah, okay. Let's see it. What's in there? GNU, bunch of random garbage. I don't see anything that's useful. It's probably going to be rather large. There we go. Nope. I don't see anything. I'm going to give up. Yeah, I'm going to give up. It's there somewhere on the system though. You'd have to go start, you know, on a little search, like where does Ubuntu store its standard C libraries, and then go searching for it. And then you could copy it over into your directory, and instead of using -lm, you can say, go ahead and use that shared library. By pulling it out of where it belongs though, I'm sure that you would start breaking everything. You just pulled out the linchpin for the entire structure. Yeah.
So when you GCC, it's only that same directory.
Generally, yeah.
Unless we do like link now.
Right. Oh, yeah, those are symbolic links, yeah. Okay, yeah, I'm back home. There we go. All right. By the way, how do you get home if you go down the rabbit hole of other things? CD tilde takes you back home. And now I'm at the, you know, honors, I'm at this location now. All right. But I would caution you against doing that on the CS50 IDE, simply because I don't think that you have enough access anymore that you could screw much up, but you could definitely screw up your instance of your Cloud9 on AWS, and then cross your fingers for asking them for support, because it's just a bunch of guys at Harvard that may or may not get to it anytime soon. And may or may not want to get to it to fix it or whatever. So don't go breaking stuff. Download join the Husker Linux users group, or OS2G, which is a student-led organization. Install your own instance of Ubuntu and then break it as much as you want on like a separate partition on your computer. All right, so let's identify what I did the entire time, right? So we're going to create our own financial utilities library. What we did is we separated the prototypes and documentation into a header file, a separate header file with the extension .h. And that stands for the header file, right? I'll emphasize that. We placed the function definitions into a source file with the same base file name, but a .c extension. Those are not strictly speaking required, but that's the convention. If you go and use something else, somebody's going to be like, what the hell is that, right? They're not going to be able to identify what it is because it's non-standard, right? We used include utils.h, there we go, anywhere we needed to bring in the prototypes. Right? We compiled, but did not produce an executable program using, what was the command that I used again? gcc -c utils.c, right, which produced a machine code object file. And that was utils.o, right? We compiled everything together using gcc utils.o loan.c, and then of course -lm, but that's just because we need to bring in the math library, right? So it's that compilation process that you'll be going through as we move forward to more modular code. It can get extremely complicated. If I have, and like I said, if I had thousands of functions that I've now separated into hundreds of different files, how do I compile them all? Sit there, type. Oh, I made a change to one file. Go back and repeat that entire process? No, we have yet another utility, yet another entirely different computer language called make to define how stuff is built, right? And you'll see this in your upcoming hacks and your upcoming labs where the process is complicated enough that we give you a make file. We're not going to expect you to make your own make files, but they look something like this. I don't know. Let's look at the, I'm pretty sure that lab 6 is going to have a complicated make file. There it is. Right. And this is a simple make file, by the way. But it has these rules. I want to build this image driver program. All right, these are the dependencies. It depends on, let me zoom in here. It depends on Imageutils.o, colorutils.o, and imagedriver.c. And here's the rule for how you can build it. Not only that, but it gets so complex that I actually have variables with this in this other language. CC is, what is your compiler? It's GCC using this standard, right? How do you build the Imageutils.o? Okay, here's a rule for doing that. And here are the dependencies, and here is the rule for how to build that. Make is great because it is able to determine all these dependencies. To build this thing, I first have to build this thing. Well, to build this thing, I first have to build this thing. So that's where I'll start. I'll build this, then I'll build this, and then I can build this. And it all just works seamlessly as long as you write it up as a make file here. Java has something similar. It's Maven or Ant is the programming language. It's just a bunch of XML rules, basically. Right? Yeah.
That means you don't have to recompile everything.
Exactly. You make a change, you type make, and make takes care of it for you. Right? And again, it gets complicated enough. Like for example, ignore that. That's legacy. We'll also get into more formal unit testing frameworks, and for C, we're going to be using C Maka. That means that we have to bring in, where is it? there, this library called CMACA, and to bring that in requires, here's a workaround that's even more complicated that we had to use before. We don't use this anymore, but I left it in there to remind myself how to do it if we ever need to do it again. I'm not gonna, this took me like a day of research to find all these, find out everything that I needed to do. No way am I getting rid of that, because if we ever have to go back to using that, then it's all right here. And a whole bunch of other flags, et cetera, et cetera, et cetera. Right? In fact, this is a static shared library compilation of the CMACA library that I had to build. Again, don't worry about it. The takeaway here is that when your build process becomes so complex, you need yet another utility, and in this case, it's going to be make, which has an entirely different programming language for building stuff in the C language. Right? You could do stuff like deploying too. You can have make not only compile your executables, but also compile all your tests and run all your tests. And if they all pass, then it takes your executable and it produces a downloadable zip file, and then it uploads that to the server, and your customers have access to the zip file too, right? It can check things into GitHub. All right, everything passes, check everything into GitHub automatically, and it does everything for you, right? With just one command. Of course, make files can be thousands and thousands of lines of code long. You could have conditional compilation so that, is this Ubuntu? Okay, I need to use the LM flag this way. Oh, no, we're not on Ubuntu, we're on SUSE Linux. Okay, I will use these rules over here instead. And by putting those all in one big giant file, you get away with a lot of the details. Yeah?
So does Java use something similar?
Yeah, Java has Maven or Ant. And you'll see that in your future labs as well. Right. Pretty much every language or ecosystem will have some sort of build utilities. In fact, there are build engineers. Like if you're at a large enough company, the entire build process is a whole job unto itself. Like the last job that I had, 2 people were actually employed to do this, and they did nothing but write basically build scripts all day, and because it was such a complex process. It's called, sometimes people call this continuous integration, where somebody makes a change. We need to make sure that it passes all the tests. We need to make sure that it's checked into GitHub. We need to make sure that all of this entire software development process and automating that and maintaining that automation, it's all part of continuous integration. We call them build engineers. And so you can make an entire job out of just making build scripts because it can get so complicated. Because imagine the alternative of having to type GCC over and over and over again. Well, yeah, I don't have no idea where I am anymore. So imagine having to type GCC over and over and over again, right? It's not tenable. It's not something you can do. Right? You'll be just typing compile commands instead of actually writing code. Right? So build systems, continuous integration, build engineers, etc. All right. So that's what we did in C. The process is far more opaque, I guess you could say, in Java. In Java, all you had to do was take this stuff and move it. Let me get rid of this and this. There we go. So let me go ahead and create another new class here. I'll call it Utils, similar. Oops. I'll just go with the Utils here. And I can move these things over to, Utils, right? And now it won't work over here anymore because it's no longer in the loans class. It is in the Utils class. But that's how I can separate code out. No prototypes, no compiling, because now Eclipse is taking care of that for me. No prototypes, no object files. Everything is opaque. All right. Yeah.
But still, they have to be in the same directory.
Yeah, or you would have to import them. If I put this, let me go ahead and show you what that I mean. I'm going to move this over to the default package, which means it looks like it cut and pasted. No, it didn't. Which means no package declaration. Right? Over here, the loan is in unl.cse, so I need to import I need to import utils. All right, what are you complaining about? All right, let's get rid of that. And you're fine, aren't you? That looks good. So, utils, import it. There are lots of utils. Import utils. Maybe it's not finding it because it's in the default package. So cse.utils dot utils, and then we'll go ahead and rename or put this into that package. unl.utils. There we go. And we'll move it. There we go. Now are you happy? Oh, I guess I called it UNL. .utils. Yeah, it was only griping about it because it was in the default package. That's why it's not a good idea to use the default package. Anyway. Okay. So hack 4, both C, Java, due on Monday, and it's a 401k savings, very similar to the loan amortization table that we built. Have a good weekend. I'll see you on Tuesday, I guess.